lecture series from the Chemin Bayan in the equals 8. With the, huh? So that's what we mean.
Okay, so again, very good morning. First of all, I would like to thank for the organizers of this workshop, giving this opportunity for me. And it's nice to meet you all guys here. Initially, I was thinking to present something classification results on diassociative algebras. And when I see the content of the program, I realized that there are some presentation by Prof. Shamildin on diassociative algebra. That's why in the last minute I changed my mind. In terms of diversity of our talks, so I decided to give some introduction to the left-symmetric algebras. I'm Ikrom from Unical University Kuala Lumpur, Johor campus. Okay. This research is the first step of investigation on left-symmetric D-algebras, which is a generalization of left-symmetric algebras. It was introduced recently, 2011, I think. So in this talk, I will give the definitions of left-symmetric algebra and left-symmetric D-algebras, and give classification of two-dimensional LSD, and present derivations and automorphisms of that two-dimensional algebras. Also, Rotabax operators. And the method program will be attached to simplify our calculation jobs and some future research questions and references. Okay. First is about the left-symmetric algebras. This class of algebras was studied by many mathematicians, and unfortunately they use different names for that algebra, such as Lee algebras, Wimp-Berg algebras, and causal algebras, or quasi-associative algebras. There are some literature on these topics. All this meaning the same. We are talking about left-symmetric algebras. And in 1998, Boudlet was studied this class of algebras in terms of application in geometry and physics. And in the end of the last century, French mathematician Boudlet was introduced new class of algebras which is related to left-symmetric algebras as well as classical algebras such as associative and Lie algebras. Later on, I show you the relationship diagram. I think everybody knows the definition of associative algebras. We have algebra with some multiplication, and saying that for any elements x, y, z from algebra, we have associativity for the product of that algebra. This is definition of the algebra. It previously was introduced by Prof. Ayubo. Definition of I think everybody knows. Then, in the end of last century, as I mentioned before, no new class of algebras were introduced, such as Leibniz algebra, the associative algebra, Zibel algebras, dendriform algebra, so on, where all of them are somehow related to classical algebras. Everybody knows that if we have associative algebras, if we introduce the commutator such this way, we can get the Lie algebras. This is the connection between, don't pay attention number 5, this is the number of page. Associative, from associative we will get the Lie introducing the commutator, right? Then, as looking at this definition number 3, Leibniz algebra is actually a generalization of Lie algebras, whereby if you consider anti-commutativity, then this Jacobite, Leibniz identity will become Jacobi identity. In other words, Leibniz algebras are generalization of Lie algebras. And was question that can we find some algebra where introducing new product we can get Leibniz, and meanwhile it should be some generalization of associative algebra. In this question, Ladé answered in positive way, where he introduced new class of algebras with two binary operations. Difference of significance of this algebra is we're having two binary operations with some three identities. Okay. These two products we call right and left multiplication respectively And for that, both of them are associative. Meanwhile, we have to have these three identities to be satisfied for any element of x, y, z from the algebra. Then with this algebra, with respect to these two operations, we call the associative algebra. But some people saying that associative the algebra, or shortly we can call the algebra, because D means two binary operations. And the question which I mentioned before was here: is there any algebra related to associative, and it is generalization of associative, and meanwhile introducing in that algebra new operation we can get Leibniz. So you can see here that if we introduce in the associative algebra this commutator, then this algebra becomes Leibniz. And as you can see, both operations of the associative algebra is associative, and it is generalization of associative algebra. If both operations are coincide, then these three identities gives you simple associativity of product. So it means the operations are, when operations are coincide, it means the same. And from another direction of this diagram, we can include the left symmetric algebra in this way. Left symmetric algebra is algebra with some operation satisfying this condition for any element x, y, z from A. In other words, this condition means that for the associator x, y, z, we have left symmetricity, means y, x, z. Meaning of this, and this formula is the same. And again, the same question: can we find some algebra which is related to this diagram, or where you can include in this diagram? And Philip in 2011 introduced new type of algebras, which is from this side is generalization of left symmetric algebra, from another side is generalization of the associative algebra. That's kind of algebra we call left symmetric algebra. In short, we can call it LSD or LSDA. Where we have two binary operations where we have we call right or left product, and satisfying these four conditions. We call this algebra as LSDA. All right.
So what does it mean? The second x, y, z with
This one.
with comma, yes, this one.
This one.
This three, yes. What is it?
Yeah, this is associator.
Association.
Yeah, associator. If associator is left symmetry, means x, y, here y, x. That we call left symmetry algebra. Actually, there are notion of right symmetry, where our associator will be right symmetry. Yeah, associated. Okay, if you have these four identities for these two products that satisfying these conditions, you have a left symmetric algebra, which is generalization of left symmetric algebra. Right? How we will get left symmetric algebra from this? If and in left symmetric algebra, both operations are the same, as shown in this slide here, then we will get these four identities gives you only one identity, right, from this side. From another side, for if in left symmetric algebra, both operations, left and right product, are associative, then it becomes the associative algebra. So, okay, let me explain somehow in diagram. Let's say this is LSDA. Please correct me if I'm wrong. Here I have the associative algebra. Here I have left symmetric algebra. Here is associative algebra. The LSD is generalization of the associative as well as left symmetric algebra. And you can see this diagram. It shows the relationship between the classical algebras, associative and with new types of algebras. I guess looking at this diagram, we can see that the study of this type of new algebras is very significant as a mathematician. Because sometimes when I talk to my colleagues where I'm working in technical university, most of them are engineers and they are asking me why you are studying all this. One of them asking me 1 plus 1 is 2. Then what you are doing, all mathematicians, what you are doing? I said, sorry, I can't answer to your question. Because all of us, they are looking from the application part, but we are looking at the theoretical concept of these algebras. Okay, in early stage of any class of algebras, classification is very important. It's very important to find some examples of algebra, at least final dimensional case, at least some classification results are very important. That's why in this talk, I will give you a classification of two-dimensional left symmetric algebras. But as I mentioned before, left symmetric algebras have been used different names. For instance, Weinberg in 1963 studied this class of algebras as left symmetric algebras. But meanwhile, Haber studied this identity, which I was shown before, and he called this algebra as privily algebras because of relationship with the algebras. And causal, yes.
Why the condition not necessarily associated, not necessarily for condition? Why this condition?
This is the general definition of LSA, sorry. Not necessary to be finite dimensional because it can be infinite dimensional algebra, not necessary to be. And if you associate if you satisfy the left symmetricity, then we call left symmetric algebra. And Koszul and Weinberg, they use this algebra as a Weinberg algebra. Some books using as a Koszul-Weinberg algebra. And Cooper-Schmidt, 1994, also considered this algebra and he called them as a quasi-associative algebra. But actually, all this is the same. Unfortunately, they use different names. Here are some examples of left symmetric algebra. Let's consider some commutative associative algebra A with multiplication. If we introduce this new product, let's say star, as x times dy is a derivation of element y, then this respect to this star operation, this algebra satisfies the condition of left symmetric algebra. A very simple example of LSA. Second example, if you consider vector space or field F with the usual product, and if you consider some elements fixed for vector from A, then if you introduce new product such this way, then you can easily check that this product satisfies the identity of left symmetric algebra. Example number 3, if you consider associative algebra and linear map satisfying this condition for any element x, y from associative algebra A, and this defines the left symmetric algebra. And R, in this case, we call Rhoda-Baxter operator with weight 1. Let I give you the general definition of the Rhoda-Baxter operator. This one is with weight 1.
In example 2, that one is not usual product, it's a linear product. Linear product. Yeah.
This one.
Linear product. You will get vector you will multiply by number.
Yeah.
Another vector also multiply by number. Then adding you will get another vector. So that's why that is the linear product. You cannot multiply two vectors.
Yeah.
That is linear product. Yeah. It must be, result must be a number. Element of x.
Here are some results relating to classification of LSA. So first was investigated by Bay, 1996, who classified two-dimensional complex left symmetric algebras. Method was basically the computation of the structural constants. And later, some other mathematicians also did some classification results. I think to read all. About the left symmetric algebras, the definition already given above. And now examples. As I mentioned, any associative algebra can be considered as an example of left symmetric algebra. And if in differential symmetric algebra, if we introduce right and left product this way, then we can check that algebra A respect to these two products satisfies the condition of left symmetric algebra. As example. Next example is the polynomial algebra kxy over 2k. Then if we define two products in this way, then we can check that this polynomial algebra respect to these two products is the left symmetric algebra. In this example, the polynomial algebra dkxy introducing such this multiplication had been shown before in 2010 that it can be considered as example of the algebra as meanwhile as example of the algebra. Let us consider left symmetric algebra and M and N subset of S. We define the diamond product of M and N by this way. Okay, there were right and left product of subset N defined in this way, this formula. And actually, the purpose of introducing this diamond product is we are willing to introduce the notion of nilpotency in left symmetric algebras, as we did for D algebras in 2010. We have to consider the following series as usual, and we will identify the notion of nilpotency. Left symmetric D algebra S is said to be nilpotent if there exists natural number T such that S to the power T equal to 0. I think this everybody aware about this definition because it's standard way how to define the nilpotency. And it's observed that the sum of two nilpotent ideals will be ideal will be nilpotent. And a less symmetric algebra S is the associative algebra if only if the products of S are associative. Right? When we have, as I mentioned before, in LSD, if you have associativity of both operations, associativity, then it becomes the associative algebra. This proposition can be checked very simply, straightforward calculations by substituting into the identities of the algebras. And left symmetric algebra, let's say S is left symmetric algebra, the following commutator define the structure of this algebra, and this theorem also can be proved by straightforward calculation. Here, the classification of two-dimensional left symmetric algebras. First, we introduce the notion of multiplication operators, right and left. We have two products, that's why we have to consider four operators, two right multiplication operators and two left multiplication operators. And the following left multiplication operator is called the following identities. Also, straightforward calculations can be proved these identities. Similar properties we can check for the right multiplication operators. And we define the right and left manipulators in this way. This is respect to left product, this is respect to right product, right manipulators and left manipulators. In general, the manipulator of the left symmetric algebra we define in this way. As an intersection of right manipulator respect to left product and left manipulator respect to right product. that intersection is an operator of the left symmetric. We need this definition because when we prove the classification, we will use the anophelators. Right? Let's consider as a left symmetric D algebra n-dimensional over complex numbers with basis E1, E2, An. This is the multiplication product of basic elements where gamma ijk, delta ijk are structural constants. Usually when we start to classify any finite dimensional algebras, usually we start to calculate the structural constants. Standard way to find examples of finite dimensional algebra. And by using the identities of LSD and formula number 1, we can prove this lemma. The structure constants gamma ijk and delta ijk of LSD have the following relationship. This lemma also can be proven by strict calculation of substituting this formula into the identities of LSD. Proposition. Let vector space S is the left symmetric D algebra with respect to these two products, right? Then the following assertions are equivalent. So the associative algebra is important, left symmetric algebra is important. And the final result for this section is the classification of two-dimensional LSD algebras over complex numbers. We found 6 parametric non-isomorphic class of algebras in dimension 2. As you can see, algebra number 1 with 2 parameters, algebra number 2 also with 2, and so on. Each algebra has some class of algebras with some parameters. And here, the isomorphism criteria for these algebras easily can be checked that for some parameters of algebras, for some parameters, we will obtain the associative algebras which we classified before. And here, in this table, for instance, this table represents the isomorphism criteria between algebras for different parameters. For instance, algebra number 1 will be isomorphic to algebra number 3 when parameter A equal to 0. If not equal to 0, they are not isomorphic to each other. And let's say in this case, algebra number 1 will be isomorphic to number 2 if A equal to 1 from the algebra 1, and from algebra 2, parameter C should be equal to 0 and parameter B should be represented like that equation. Then you will have isomorphism. For other values of the parameters, they are not isomorphic to each other. And derivations of LSD for that two-dimensional case. I think everybody knows the definition of derivation, but difference for this case is as long as we have two products, we have to consider two identities like that way. The xy in respect to right product and as well. Sorry. Copy paste typing error. Sorry for that. Should be this one should be respect to left product. Sorry for that. And we can check that A at Z x, where we define in this way, is also a derivation, and such these derivations we call inner derivations, as presented by previously before. So left symmetric D algebras are said to be characteristically important if the set of all derivations is important as an algebra. Here, the derivations of two-dimensional algebra, which we classified before, this is the derivations. Here, the group of automorphisms. Here, we can conclude that there are only one characteristic important left symmetric D algebra in dimension 2, which is algebra number 2. And there are some sub-algebras, sub-classes. If for any x from S, right multiplication operators, both. As you remember, we defined two right multiplication operators with respect to right and left product. If they are important, then S is said to be transitive algebra. If S has no ideals, except itself and zero, then S is said to be simple algebra. I think everybody knows the definition. And if for any xy from A, right multiplication operator respect to right multiplication operator is satisfied this identity, it means if it's commutative, then this algebra we call Novikov algebra. And lemma from the theorem 7, where we describe the algebras, you can check that there is no commutative LSD algebra in 2-dimension 2. All 2-dimensional LSD algebras are not transitive. None of them is important. And there are two Novikov algebras among the 2-dimensional LSD described above, which are algebra number 2 and algebra number 3. Next is about the rotavex operators of LSD. I think this definition I was given above, but it was with weight 1. This is the general definition of the rotavex operator. Usually, rotavex operators have been studied for less symmetric algebras in 2007 by Lee. That's why I tried to do some first initial steps to study on how to calculate the rotavex operators of finite dimensional algebra. That's why, considering the multiplication of basis elements, AI, AG, respect to left and right product, we have structural constant as above, and operator can be represented by this summation. Then you have this table. The rotavex operators of the 2-dimensional left symmetric algebra are given in the following table. This program, Maple program, will help us to identify, because when we classify, as we mentioned before, we will work with the structural constants. In the end of the day, we will find some product of basis elements, some multiplication table, in order to confirm whether that algebra is satisfying the condition of the LSD or not. We can use this Maple program to check, just to check the identities. Once you get the multiplication table, you can run the program, where in this program we will use the multiplication table as a 3-dimensional vector, and this program will check for you and identify whether that algebra which you found is satisfied the condition that the identities of LSD are not. Very simple program. For instance, let's say you have LSD 1, where multiplication table is E1, E2, respect to left product E1, E2 equal to E1, E2 equal to E2. Then respect to another operation is E2, E1, E1. We have parametric here, sorry. A E1 and E2 is B E1, and the last is E2 equals to E2. If you have this algebra, which is in our case LSD number 1, then just we can check key in this multiplication table in terms of 3-dimensional vector. This is respect to first product, this is respect to second product, and run program LSD1. LSD1 is respect to first product, LSD2 is respect to second product, and dimension 2, then the program gives you whether this is less symmetric algebra or not. Why I was, in the beginning of my talk, I said that in the last minute I changed my mind to change my topic, because this is very new class of algebras. Maybe someone interested to study about it, to do some research on it. So there are many problems because it was introduced recently and nobody touched before about the structural theory of this algebra. That's why you can do some classifications, you can consider the importances, simple, you can consider simple algebras, introduce the radical of algebras, you can consider, study derivation, automorphisms, and too many problems to be studied. So this is the questions for the future research. All right. This is the definition. That's all. Thank you very much. Okay, when you study the result, the properties, the feature, the nature of right symmetric will be similar to the left symmetric. That's why it's enough. Because you can say that some literature, they study right symmetric algebras, which is the result of the similar. That's why it's enough to consider one of them. Usually we call opposite algebra. Right symmetric is the opposite of the left symmetric.
And the reason because it's symmetry.
Sorry?
And the reason for this, because it's symmetry. The results will be same.
You may check the when you consider x, y, z associated is y, x, z. Then for the left, for the right, you have x, y, z equals to x, z, y. When you extend, as I given above the formula, I think the formula would be similar. To be honest, I don't know what is the reason why it's similar, but I know that no point to study both. You may study only one of these two.
Let's take this new class of algebra.
The symmetric?
Let's take algebra. This new class.
Yes.
What's the reason to give this new class?
Okay, the reason.
Why they give it?
Yes, why they give it? First of all, first reason is they are very close related to Lie algebras because an associative algebra. Associative is classical. We are learning associative from the middle of the 19th century. Too many things can be applied in associative algebra. And Lie algebra, if you interested on application, you can see some application of Lie algebra in physics, other branches of mathematics as well as physics. So, but currently, sorry for interrupting you, currently we don't have so much application, but Burde in 1998 studied application of LSA in geometry and physics. I can give you the paper, you can study why. The reason being is they try to find the first reason is they are related to these algebras. Second reason is the application of that algebra.
I'm very interested to know one thing. I'm very interested.
All right.
Lie and Leibniz is generalization for associative algebra.
Not really. Not really. No. Because from the associative, we introduce the. If you have associative algebra, if you introduce the commutator x, y, z, x, y minus yx, then you will move to the Lie. It's not generalization. It's another class of algebras where you will obtain introducing new product. But Leibniz is generalization of Lie. Yes, Leibniz is here, bigger than Lie.
Why they give it? After we study Lie. Why after that we study Lie? I'm sorry for really I'm interested in this.
Because another question is not related to this. Maybe then after we can discuss it. Then, any other questions?
Yes.
Table for the graduation. What is it? Table for graduation of the
Yes. Okay, sure. Yes.
Then if you take algebra 6,
Yeah.
it means they have the same dimension. Both dimension of graduation and dimension of provision are the same. Is
Yeah.
there any relationship between the two?
I haven't checked it. this table just represents the derivations and automorphism. And the relationship between them, I don't know.
No, there is such a general question is related to the relation of derivation algebra and automorphism group.
Okay.
Then different. If you add them, the result must be n squared. So that's why here if you add only 2, not 4. So that's why we wondered why it is 2. Derivation algebra dimension is 1 and the automorphism group dimension also is 1.
Yeah.
It must be 3. If the derivation algebra dimension is 1, then automorphism dimension must be 3. Something like this. Because the different derivation algebra dimension is n squared minus the automorphism group dimension. So that is regarding that relationship. So there's some kind of introduction.
It might be checked.
Check.
Yes.
So when you doing the derivation, which method you are using?
Sorry?
Which method for calculating for this derivation?
Which method? Just I consider D1 as a D11, D1, D1, D2, and I check the multiplication of multiplication table of each algebra, then I found this. Because this one represents your matrix, right? 2 by 2 matrix. By using this formula and substituting into the multiplication table, I got this 2 by 2 matrix. I didn't apply any method or anything, just straight calculation. Yes.
Classification of two-dimensional algebras is not special, general.
Okay.
Maybe you can use them to get the results for not only over complex number, over any field.
Perhaps correct, but we'll have to take note that we're having 2 products instead of
There
one.
is, for one of them you have classification, for second one also, only you should check some is your axioms.
Yes, right, you're right, agree. When we classify the associative, we do the same thing what you see now. We have the classification of associative, and because associative means respect to one operation, you have the already classification table. And respect to second operation, we consider general, and we play with the identities of the algebra in order to get the final list.
Have you considered the characteristic very important for
Yes. Only one. Number 2 is characteristic.
numeracy efficiency?